Okay, let's see. How's the? Yeah. Okay, cool. So last time we were talking about curl, and remember this is a kind of arguably premature, but let's say preliminary, right? Put a positive spin on it. I've been introducing ideas which I'm not really going to be able to justify here, right? So the purpose of this is to kind of plant thoughts and allow certain kind of images to be kind of settling in your minds. So again, we define this thing called curl that we denote with that expression right there, computed by this formula. Again, taking a symbolic interpretation of this as being a cross product, as it were. Again, flexible with the notation. And I've made this claim that what the curl represents is, in some sense, how much and around what axis the fluid circulates. To what extent is there kind of this sort of thing? And that's literally hand waving. So here's our first example, and we talked about this one last. I think this is where we ended last time, and maybe you can see kind of the circulation happening there, right? And that is, let's see here, represented by the curl, which we computed to be 002, and notice that by way of its direction, the curl pointing up, that indicates that the circulation, I'm being deliberately vague as to what I mean by that, is kind of around the z-axis, which of course you can see right there in the field itself. So this is a nice starter example for understanding what curl looks like, because it really is geometrically visible. Yeah.
What's the magnitude of the vector have to do?
Yeah, so that's one of these things I'm not going to be able to talk about precisely yet. So the greater the magnitude, the higher the category of the tornado, basically. So now we don't have any units on here, right? So I can't really make that. I can't be too explicit about what I mean by that. But if these field vectors were longer, like if there was an extra factor of 5, let's say, in the vector field here, right? Then the curl would be longer, right? Would have a longer curl vector, and the field would be more dramatic, as it were, and that would represent in some sense anyway, a more powerful vortex. So twisting of the fluid around the axis. Is that cool? Is everybody happy? Yeah. Okay. All right. I think this is where we quit last time. Okay. Another example. Now this is another one I think is pretty satisfying. You look at this picture, you don't see anything that you'd want to call circulation here. After all, the field lines are all straight lines, and it just kind of feels like, and I guess they're going this way over on that side, but there's nothing round in the picture, so it doesn't look like there ought to be any circulation, and so we shouldn't expect to see any curl. And computing the curl, you get 0, as expected. Okay, is everybody happy with that? All right, the next example I think is really nice, really important, and it shows one of the real subtleties of what curl is. I've been, again, deliberately vague about how I describe curl, and I've been air quotes, circulation, and kind of this kind of thing. I want to distinguish between, let me come back up to this picture here for just a moment. I want to distinguish between what the fluid is doing, what a particle within the fluid is doing, versus what if something were sitting in the fluid, how would it be behaving? So now in this case here, there's not much of a distinction, because if I were to plop a floating thing into this fluid and let it sit right here at the origin, well, this fluid that's rotating around would make that thing rotate around as well. So they're both there's a rotational aspect of both the fluid and something that's sitting in the fluid. Now, by contrast, though, let's think about this picture right here. We'll just look at the picture first. We'll get to the algebra in a minute. The flow lines are all straight lines again. Right? All straight lines. no particle moving through this, no particular piece of this fluid, I'll say, is rotating. But think about what would happen if I were to have a perfectly balanced, buoyant thing right there. And what would happen to it? Well, on the one hand, fluid is going by on one side in that direction. But on the other hand, over on this other side, the fluid is going that direction. And I pose that while no piece of fluid is rotating or curving in any sense, nevertheless, that ball that I have right there would be rotating. Right? Because it's being in some sense, it's being pushed what you might call clockwise on both sides. Everybody see that? So that's kind of a weird thing. Very hard to see it from the picture itself because, again, the flow lines are all straight. Right? So this is one of the cool things about curl. Curl detects this because, again, you can take this vector field here representing that fluid flow. You compute the curl. You get this, which of course points down, and as we discussed previously, thumb in the direction of that curl, look at the fingers, and sure enough, that is indicating how this orange ball would be rotating inside of that fluid. So there's kind of a hidden circulation in this vector field. Yeah? Mm-hmm.
So visually, how is that not the same for the one above?
Yeah, well, that's right. Okay, so let's think about the one above here, and let's imagine some little ball, let's say right here, right? And, well, the fluid is going the same direction on both sides of it. And so this little orange ball might start moving or something, but in terms of, would it be rotating as it moves? Nah, it's being pushed kind of the same on both sides. Is that satisfying?
Yeah.
Yeah, cool. Everybody good? Okay, so yeah, curl is there's a subtlety to it that is a little bit hard to describe. We're going to make all of this much more precise in Chapter 7. So this is all just preliminary. The last thing I want to talk about, and I really need to be brief on this, this is also really premature. This is also some stuff that's not really quite in the book. At least not the way I'm going to present it here, and not as much as I'm going to present it, when we get to chapters 6 and 7. It turns out that there are relationships between gradient, which you'll recall is an operator that turns functions into vector fields, and curl, which is an operator that turns vector fields into other vector fields, and divergence, which you'll recall takes vector fields and results in functions. And if you fit them together like this, notice the Legos fit. If you put them in this particular order, what comes out of gradient is appropriate to what goes into curl and all that. If you put them together in this order, some kind of amazing things happen. And it's not a coincidence, as it turns out. In fact, a better way to say what I've got written here is that there is actually a more sophisticated construction that I can't even tell y'all in the context of Math219, which, if you look at the special case of three-dimensional vector fields and all that, would in this context be gradient, and that same thing in this context would be curl, and that same thing in this context would be divergence. And I know that sounds mysterious and weird, and I'm doing that on purpose because the reality is far too inaccessible for this class. But so anyway, I want to point out that this is not a coincidence that great things happen when you compose them in this order. This is actually evidence of a unifying principle in the background that, again, tragically is just too much to talk about in this class. So my goal in showing you this is just to kind of persuade you that there's a really good reason to want to do this, to pop them together in this order. And so I'm going to show you a couple of things about it. Let's see here. Here we go. And I can do this. There we go. That helps it fit. This equation right here, easily confirmed from the algebra. No sweat. You just take a function, compute its gradient, take the curl of that gradient, and what you'll find is that you will always get 0. Now, let me represent this algebraically. If you take the gradient of a function, and then if you then take the curl of that resulting vector field, the result will always be 0. Okay, and so I'm gonna describe this with a particular metaphor that I like. The metaphor is, I'm gonna call this a lifetime. It's a metaphor. And the idea was that this function was, I'm going to say, born there, and it survived to here. I'm going to say it died here. What I mean by die, I mean 0, right? Kind of, very loosely speaking, kind of like death in a way, and furthermore like death in the sense that no matter what you do to it, it's still 0, right? There's no coming back from it, as it were. A little bit of a dark metaphor, but I think it works actually really nicely. So it turns out that all lifetimes in this, when you set things up this way, all lifetimes are 2. Just like this particular example. So there was a function that was born here and died 2 steps later, lifetime of 2. Okay, here's another example of that. Just cleaning up here. Another example of that. Suppose you have some vector field here, and suppose that if you take the divergence of it, you get 0. I claim that that vector field, that same vector field, must be the curl of some other vector field. It must be the curl of something over there that I'm going to call G. And so again, look at this. We have then another lifetime of 2. Right? So in other words, what this theorem is saying, from the point of view of the lifetime metaphor, is that this vector field here, whose divergence was 0, this could not have been where it was born. It can't be that it doesn't have an anti-curl. It has to have come from something previous. Otherwise, its lifetime only would have been 1. And that's not possible. All lifetimes are 2. It's hocus pocus, mystery magic, until you see the more sophisticated stuff that, again, we can't do in this class. It's far too much for this context. So anyway, nevertheless, the fact, and so I'm just going to claim that this is true, and we're not going to be able to prove this as a general result, but the fact, if you're willing to believe me, that all lifetimes are 2 when you compose these operators, I hope is persuasive that there is something fundamentally natural about composing them in this order like this. How else could this mysterious, oddly consistent pattern be true if there wasn't something deeply good going on with this composition? Yeah.
When you say first of G, do you mean non-zero G?
No, not necessarily.
Okay.
It could be 0. But the thing is, if this were 0, then its curl would also be 0, which would mean that we were looking at 0 in the first place. But what I'm saying is that there can't be some situation of a vector field here where the divergence is 0, but where there is no vector field whose curl is that thing. That can't happen.
Okay.
Yeah. Okay. Now, just for self-defense purposes, I am going to point out the asterisk here. This asterisk, I am making certain assumptions. I'm assuming that everything in sight is as differentiable and continuous as it needs to be. So there are some nasty issues that come up with vector fields that have discontinuities, singularities. Things get a little weirder, and so that does throw a wrench in the works. But if everything in sight is continuous and differentiable and there's no problems with that, Then the only remaining exception is constant functions. Notice if you have a constant here, its gradient is 0. It's a sad story, right? But this is the only, other than regularity issues, this is the only counterexample to the lifetime of 2 result. Okay, so again, this is just to kind of raise your eyebrows that this is a fundamentally natural thing, and we'll do much more with this as time goes on. And likewise, there's going to be various other connections and relationships and analogies between these operators. Okay. All right. So moving along into Chapter 5. What happened to Chapter 4, you may wonder? We are going to do Chapter 4. It's just going to be at the end of the course. And the reason for this is that as much as we can, that we can push to the end of the course, allows me to pull chapters 6 and 7 earlier in the course. And this is valuable because chapters 6 and 7 are the most challenging part of the course. That's where things get kind of intricate and connected, and there's multiple points of view, and it's very challenging. And it's good for students to have as much time as possible to digest that stuff. So chapter 4 is really the only thing I can push to the back. Everything else in the course is kind of prerequisite to 6 and 7, and I feel like I can't really do it. Okay. All right. So 4 will come later. On to 5. Okay. Y'all will recall in Chapter 2, very first thing we did is we talked about partial derivatives, and I kind of apologized very first thing and noted that it's really not the best way to start talking about derivatives. I mean, deep down, if you really want to talk about what is a derivative and what's the best way to think about multivariable derivatives, it's not partial derivatives. Partial derivatives were a kind of first crack at it, and that had some value, but it's really pretty limited. And hopefully now you're comfortable with my assertion that really the derivative matrix that's really the best way to think about a derivative in a multivariable setting. Any input vector turns into any output vector by way of multiplication by the derivative matrix. Okay. So we started with partial derivatives because it was easy, and the book did it that way. So just like that, we're going to do the same thing with integrals. I'm going to start, because the book does, and pros and cons, but we're going to start with what I think is a I guess reasonable first step, but ultimately not the best way to think about multivariable integrals. All right. So again, just like with partial derivatives, please don't hang your hat. Please don't make this your cornerstone point of view on multivariable integrals. This is not the right point of view. Okay. That said, let's see here, back to there. So y'all will recall this kind of a problem, volume inside of a rotated surface. If you have a graph that you rotate around to make a surface, and you want to compute the amount of volume contained inside there, like so. Hopefully y'all remember this strategy. Big idea is that some little piece of volume there, right, you can understand that piece of volume pretty easily in this case, because we can look at the cross-sectional area. The cross-sectional area is no problem to compute. That cross-sectional area is just a disk. Right? The area of a disk is easy. And then we multiply that cross-sectional area times the thickness down here. That thickness dx. And area times width, if you will, gives us that little piece of volume. And then, of course, you add... Oh, whoopsie. I wanted to be in the highlighter mode. This piece of volume is what you add up over the whole interval from A to B. Does that look familiar to everybody? Yeah. Okay. All right. I'm going to steal one of the ideas from here, and that is that if you're interested in adding up volume, then you can take slices, and each one of those slices has volume, which is area, times thickness. I'm just going to use that same strategy to try to now answer a different question. Here, this is no longer a rotation. This is now a graph. Graph of a function of two variables. Can't really do this in a single variable calculus class. Right? And this time, we're not going to talk about what's inside. We're going to talk about the amount of volume that's underneath that graph. Nevertheless, still a volume, and so reasonable that I might want to compute that volume by slicing it into pieces. So there's a piece of volume. And I could reasonably claim that couldn't I compute this volume as being the cross-sectional area here and multiply that cross-sectional area times the thickness. Wouldn't that be reasonable? Area times thickness would give me a piece of volume that I then add up. Cool. Here's the problem. This cross-sectional area is not a garden variety, high school geometry thing, right? I mean, we really critically relied in this calculation on the fact that cross-sectional area was a familiar object, namely a disk, and the area of a disk is easy. This is not a disk, it's not a square, it's not a rectangle, it's not a triangle. So a lot of people would throw up their hands and bail at this point. We're going to press on. And it turns out that even though it's not a garden variety high school geometry formula, it is something we can deal with. And in particular, if you look at that curve, right, this is the part of the original surface that's in that cross section. And you realize that what we're looking for is the area sitting under that curve. How are we going to compute that area? Well, area under a curve. We've heard that phrase before, right? Area under a curve is an integral. And now, quibble, you can only do that if the curve is a graph. But really, this kind of is a graph. Because keep in mind, we're looking for the area of that particular cross-section, which means we're looking at a particular value of y. This y right here is set. It is at that one single value of y that I want to compute this cross-sectional area. So as I compute this area, y is a constant. And if y is constant, then it's constant inside of this expression here, which means altogether, in fact, as we had perhaps hoped, height, z, is a function of, well, just the one remaining variable x that tells you how far you've gone along this way, or if you want to think of it for that y coordinate, how far you've gone along this way. We literally have height as a function of horizontal, x direction, which is horizontal in this direction. So this is literally a graph. We want to compute the area under a graph, and area under a graph is easy. Area under a graph is just the integral. How we doing there? Everybody all right? Yeah.
So would you be able to see this without drawing a picture, or do you need to draw a picture?
I need to draw a picture to see this myself. Yeah. Now keep in mind specifically here we're thinking about this one very narrow question of finding volume under a graph of a function of two variables, right? So this is strictly a volume question, so I need the picture. Everybody okay? Okay, now here's where a lot of students get thrown. you look at this expression here. We have an integral. Okay, now y'all know integrals. Integral from a to b, right? Dx, no problem. But you've probably never seen a function of two variables inside of an integral before, or you may not have. Probably have. So that seems weird. What do I do with the y there? Isn't y like a function of x? Or how do is there a chain rule to be used here? How do I deal with the y? Right? And reminder, don't forget, y is fixed. Y is to be treated as a constant. Y has to be fixed because we have to settle on a single value of y, at least at a time, in order to even know what area we're talking about. So as we're computing this area, y doesn't change. Therefore, this is an illusion. It looks like there's two variables in here, but there aren't really. Y is a constant. Everybody good on that? So this is, in fact, just an integral of a function of x, dx. Yeah, there's a weird-looking constant in there, but it's integral function of x dx. And we can totally do that integral. Everybody happy? Okay. So once you know that area, right, then the volume, going back up to here, let's see, you know what, I think I mixed my colors up here. We were looking to compute the volumes of these chunks here. How would I compute that amount of volume? Well, the volume is area times thickness. The area is that integral. The thickness is, the thickness is like this. The thickness is in the y direction. So integral and then times dy. We add that up for all values of y, and there we go. We have an integral of an integral. It's kind of a weird construction when you really look at it, but that gives us what we want. Total volume. Everybody happy? Got examples to follow, of course. Okay. All right, now I've got a mess. So let me clean that up. Let's see here. A couple of things. Oh, terminology. This is called an iterated integral. Again, not really the best way to think about multivariable integrals, in my opinion, but this is our good little first step, and it's going to end up being useful also, so there's really no harm in doing it first, I suppose. But again, don't let this be your fundamental point of view on integrals. So let's see here. A couple of things to talk about with regard to these before we do one. There's two integrals. It's tempting to say one of them's first and one of them's second. And here's the problem with that. We wrote down the y integral first. Right? Because as we were slicing things up, the very first thing we did is we sliced perpendicular to the y-axis. We wrote, integral dy, but then we had to figure out what was on the inside. And then it was second that we got to realizing that our integrand is a dx integral. So we constructed this with the y integral created first, the x integral created second. But when it comes to computation, I have to evaluate the dx integral first. I can't do the dy integral first. I don't know what its integrand is. The dy integral has an integrand that is itself the dx integral. So I have to do the dx integral first just to see what my dy integrand is, and then second, and only second, can I do the dy integral. So which one's first or which one's second? Not clear, right? It's kind of ambiguous. So that terminology is, I think, to be avoided. People won't know what you're talking about. There's a huge potential for confusion. So, go ahead.
So are you not allowed to flip it?
We'll talk about that later.
Oh,
So right now we're doing a very specific construction here, right? We made and I know where you're going, right? It's a good thought, but we're starting by slicing first perpendicular to the y-axis, We made, this construction as a result, and this is all that we know right this moment. Yeah, so you're getting a little ahead. Yeah. Okay, so please don't use the term first and second. Doesn't make any sense. It's unclear. What you can do, and what is totally clear, is you can talk about which one's on the inside, right? dx is on the inside. And that answers, in some sense, both questions. If you say the inside integral, well, yeah, that's the one that I generate second and I evaluate first. That's how inside works, right? And then there's the question of what's on the outside. Well, again, perfectly clear, unambiguous. All right. Next, it's easy to lose track, and per your question, if you don't have a picture, right? If you're not looking at a picture right away, it's easy to lose track of the fact that for the purposes of this inside integral, the dx integral, where we're computing the cross section, right? It's easy to forget that y has to be treated as a constant for the purposes of that inside integral. Said differently, the outside variable is the one that's to be treated as constant, right? So nice little rule. Notice that with when you phrase it like this, no picture required. When you're working an inside integral, the outside variable is to be treated as a constant. Okay. All right, and let's do one. Okay, so we are going to compute a volume under a graph. I'll do it like that. Volume under a graph. Here you go. Now, specifically, you'll notice it says volume under the graph sitting over this rectangle here. Now, how have I denoted that rectangle? I've denoted that rectangle like this. This is a very handy notation for rectangles. The first listing here, 0 to 1, is telling you the range of values of the first variable x, and the second interval listed there, 1 to 2, tells you the range of values of the second variable y, and you can see if you know the x sort of shadow, right, and the y shadow, then that uniquely describes the rectangle. Does that make sense to everybody? Handy notation. Heads up, be on the lookout. So now, good news, we don't have to reproduce the argument that we've already gone through. We already established that the volume, here it is, the volume is this iterated integral. We could just cite that. Volume is that iterated integral, and now off we go. It's a matter of doing computations. So let's see here. We'll start again by focusing on the inside integral first, as we must. And let's see here. Doing an integral of x squared gives me 1/3 x cubed. Yawn, right? Old news. And here's the landmine. A lot of students will look at that y squared and think, hey, 1/3 y cubed, right? Because that's how the symbolic manipulation works. But you got to realize this is a dx integral. It is not a dy integral. Y is the outside variable. Therefore, y is to be treated as a constant. Therefore, y squared is just a great big constant. And the way you take an antiderivative with respect to x of a constant is just constant times x. Does that make sense to everybody? You can see why this is dangerous. Lots of students mess that up. So, heads up, right? This is part of your job as you're evaluating iterated integrals is to keep track of, wait a minute, which variable is actually a variable and which variable is to be treated as a constant. Okay. The other little landmine here I'll point out is concerns plugging in. We have these values here, 0 and 1, that you see here, 0 and 1. And we've done the antiderivative, and now we just have to plug those values in. And so let's see here, for example, this 1 here, we plug it in. And then what a lot of students will do, just kind of, not thinking carefully enough, is to also plug in this 1 representing the ending value of x, but are just kind of plugging it into all their variables and will accidentally plug it in for y. And of course, that's not at all appropriate. Y is a constant, right? Y is not what's varying for that inside integral. Y is a constant. We just treat it like a constant. And so there is no plugging in to be done for y. That y squared just stays y squared, right? And so altogether then, let's see here, all of this turns into that as we're plugging in the upper bound x equals 1. Is everybody on board? Everybody see the landmine? All right. So my own little personal workaround on this, my mathematical life hack, is I like to actually explicitly indicate that because x is my variable that I'm plugging in for, I explicitly indicate x equals. That that's the variable for which I am plugging in these values there. And I find that that's helpful, at least to me, to keep me from inadvertently, if I'm not paying attention, not being careful enough. This cuts down on my error rate by a pretty good factor. So that's not required, but I do strongly encourage it. And it costs you what? Half a second to write x equals, right? It basically costs you nothing, and it will spare you big problems. Okay. So, I plug in x equals 1. It turns into this. You plug in x equals 0. It turns into that. And now we've got a single variable integral. Notice the y's are all the x's are all gone because they've been integrated out. We plugged in what the values of x are, 1 and 0, thus leaving an integral with only y, and that's just a straight up single variable calculus integral, no problem, nothing to it. Everybody happy? All right. Okay, so now somebody asked, you asked about can you do it the other way? What if you slice first in the x direction? And let me go back to the picture and try to draw approximately what that would look like. Instead of slicing perpendicular to the y-axis, like we did here, what if we were to slice perpendicular to the x-axis, thus giving me slices that would look kind of like this? Again, perpendicular to the x-axis there, and then letting x go from A to B. Well, then those little slices would have a thickness that dx. There would be a cross-sectional area that would be a function of x, the computation of which, for a constant fixed value of x, would be an integral in the y direction. So notice it's a lot like the calculation we just did, but just the x is playing the role of the y, and the y is playing the role of the x. It's just kind of a little switcheroo, right? And you can go through, and by the way, I think everyone should go through, think through these pictures, draw this picture, do the analogous to what I've got here, and persuade yourself that what you would get where we previously computed the volume as this, by slicing in the other direction, you would compute that same volume and get this. It's a really healthy exercise to make sure that you can draw the pictures, do the algebra, write it down, have it make sense, and come up with this result. Now, there is a nice little shorthand to notice about this alternative, and that is that the dy integral that was on the outside goes into the inside. Notice both the differential and the bounds that had been on the inside are now both on the inside. And then likewise for the, whoops, there we go. Likewise for the x differential and bounds that had been on the inside, those go to the outside. And so it's this move right here. Right? And this is totally fine. Very convenient. Now do make sure that you don't do this. That's no good. It doesn't make any sense. Right? If you switch the differentials, you've got to switch the bounds too, for sure. Okay. And now just a warning and the preemptive of a problem that we're going to encounter later on. Everything we've done so far is over a rectangle. We are eventually going to be able to deal with integrals where the domain is not a rectangle, and we'll talk about that a little bit later. When we have that done, this little switcheroo move only works when the domain is a rectangle. Once you have a non-rectangular domain, forget about this move, right? Nothing of the sort makes any sense in any way, ever, if it's not a rectangle. Okay. All right. Okay. So, yeah, question. Go ahead.
How do we know the domain is a rectangle?
Oh, that was the premise. Here we just started off.
Like in the notation. Like, what would an integral in which the domain wasn't a rectangle look like?
Yeah, we're going to deal with that later.
Okay.
Yeah. No, that's a great question. Very natural question, but we got enough to do yet still with rectangles. Yeah, we'll get to non-rectangles very soon. Okay, probably Wednesday. Okay, let's see. Where were we? Okay, right. So now let me remind y'all of something that we did back in single variable calculus, right? So we started with the question of area under a graph, right? It's the first thing that everyone develops in a single variable calculus class. And then you develop an integral, Riemann sums and all that. And then you notice, oh my gosh, this construction that I made to compute area under a graph, the exact same construction will compute so many other things. It'll compute if you have a one-dimensional, a rod that has a non-constant density, mass per unit length is distributed so it's in some weird way. Well, you can compute the total mass as an integral of density. And you can compute the number of bacteria in your petri dish or the whatever. There's a bazillion different things that you can compute with the exact same construction that computed your first example. And single variable calculus is very convenient that way. I'm sorry to say that doesn't work in multivariable. And I'm just going to show you a sort of an obvious first example of this. Let's suppose you have mass distributed across an area. So we're going to think in terms of mass per unit area distributed across some rectangle. And we want to compute the total mass on a rectangular sheet where mass is distributed, again, in this non-constant way. All right. Well, a pretty reasonable guess would be to say, look, this is kind of the analogous formula, right? Just like in single variable calculus. In single variable calculus, when this was height, I just kind of cross that out and put density in its place. And in single variable calculus, this would compute mass. So, hey, maybe this works here. So with, reasonable optimism, we write down this expression here and hope that this actually makes sense. And I'm sorry to say again, it doesn't. This doesn't make any sense at all. As I've written it down, right, as the development of this would have to go, this is kind of nonsense. And I want to try to explain why it's nonsense. If you look at this calculation that we did first, calculation of volume, right? And you look at the very first kind of, most on the inside, kind of the first little combination I have to do here. That is, let's see here, we have the value of the function, which is the height. And then we have oh gosh, I'll use purple. Dx, which is I'm going to say kind of a length. And what happens when you multiply height times length? Old geometry idea, that's this thing called area. Now I want to emphasize, the question wasn't about area, the question was about volume. The integrand wasn't area, the integrand was height. But integrand times dx ends up being this thing, area, which in a wonderfully convenient coincidence we already understand. Right? We understand area. That's a thing. That's geometrically known. And I can look at these little pieces of area. Let me go back to my picture here. Right? We had, let's see here, height was my integrand, and then length was my base, and these little pieces of area, well, that got messy fast. Let me just do it. Okay, these little pieces of area, I know certain convenient things about how area works. If I have a total area, I can slice that up into pieces, and the whole is the sum of the parts. This is what we say. We say that area is an accumulating quantity. The whole is the sum of the parts. Right? Boy, it sure is a lucky thing that I have that pre-existing understanding of area, because I need that pre-existing understanding to be able to develop the rest of this integral. I need to know that area, what I'm looking at here, is an accumulating quantity, because that's the very first thing I do to it, is I add up a bunch of little pieces of it. All right, fine. Now let's consider the analogous part of the process down here. And let's see here. This integrand is mass per unit area, as previously discussed. And apparently the first thing I need to do is to multiply by dx, which is a length. And here we are. We've got to figure out how to make sense out of mass per unit area times length. These don't cancel. This isn't some pre-existing idea that I already understand. Can I just assert that, oh yeah, this thing, oh yeah, the whole is the sum of the parts? Are you sure about that? Are you sure you understand how mass per unit area times length works? We've never seen it before. I guess you could call this mass per unit width, kind of. What is that? And are we sure we understand how it behaves? And no, we're not. Right? So we're kind of dead in the water here. Does that make sense to everybody? It's a nasty bit of bad news. Okay, so we're going to need a different way around then. Right? This strategy of using iterated integrals really kind of only works at this point. It only works for computing volumes. And that's not good enough. We need to compute all sorts of things. All right. So we're going to define something called a double integral. It's going to take us a bit to get down to it. I'm going to do some review first real quick. But double integral is going to be our way to resolve that matter. I want to first remind everybody about single variable integrals. Make sure to understand what a single variable integral is. The definition of a single variable integral is a Riemann sum. A lot of people mistakenly think that this is an outdated formula that got replaced by the fundamental theorem of calculus. After all, it sure is inconvenient. Right? We all have painful memories of having to crank out Riemann sums in high school calculus or whatever. And man, the fundamental theorem of calculus is so much better. So this must have come first, and then the fundamental theorem replaced it. And that's actually chronologically off by a couple hundred years. Okay? So why do we need Riemann sums? Well, Riemann sums, aside from being a meaningful definition, Riemann sums are the foot in the door that allows us to answer a bazillion different kinds of questions. Why, for example, can I write mass on a rod? Why can I write that as an integral? Well, because I can chop it up into little pieces, and I can write down on each little piece density times size, and I can then add that up, and that's literally and exactly what a Riemann sum is. Right? So we need Riemann sums so that we can connect to all of these various different applications. Whatever the single variable calculus application is, the reason it works is because we can break them up into Riemann sums. Now, what's the deal with area under the curve? A lot of people like to think of an integral as being area under a curve. A lot of people like to kind of scratch off this Riemann sum as a sort of a bad memory, right? And let's hope we can just get rid of that. And how about I'll just make a case for mass being an area. And how does that work? Right? It doesn't really make any sense. I mean, mass is a fundamentally different physical quantity than area. Why would they be the same? This is not really an argument that you can make. Now, that people will do this after a fashion, but what they actually do is they argue that you can take mass and think of this in that sense and think of this, and they make some kind of hand-wavy arguments that, in effect, create a Riemann sum, and then they say, and once you have the Riemann sum, you can reinterpret that Riemann sum as an area. But most immediately, can you go directly from mass to area without Riemann sums? No. Doesn't make any sense. So I think Riemann sums are among the most underappreciated ideas in the single variable calculus. They're actually really, really important, not just for ivory tower mathematician formalities kind of nonsense. No, Riemann sums are the foot in the door that connects you to all of the applications that you might want to do, which I think is why probably most of y'all are studying calculus. Okay, all right. If you want to hear more about this, I have a 30-minute video on the YouTube channel. It's in the miscellaneous topics playlist. It's called What is an Integral? Or something along those lines. And I'll go on at length in great detail about why Riemann sums are important. Okay, let's see here. Is it really that late already? I've got 3 minutes. Okay. So what we're going to need to do is come up with an idea for how to generate kind of a two-dimensional version of a Riemann sum. And in the same way that we'll take a single variable interval and chop it up into pieces, right? And then add up over all the pieces, right? To make a regular single variable Riemann sum. We're going to do the same thing now for a rectangle. And that rectangle, we can slice it up into pieces. And let's see here. Notice that when I slice perpendicular to the x-axis, I am also slicing up the x-axis itself, and so we see our familiar old formulas from single variable Riemann sums of delta x and x sub I. Y'all have seen that. It's just details. Y'all hopefully remember it, and anyway, it's just details. But then, of course, in order to fully finish slicing, I have to slice the other way, too. And notice that as I slice the other way, I'm also slicing up the y-axis, which gives me some analogous formulas for delta y and y sub j. Well, that's again, it's just details. The punchline, though, is once I've done that slicing, let's just get rid of the mess there. Once I've done all that slicing, then I can talk about on each individual little piece here, that little piece of area. What's going on that little piece of area? Well, it depends on what I'm computing, I suppose. But if I'm interested in computing the volume sitting over that little piece of area, well, then that would be height times the area of the base. If I'm interested in computing how much mass there is in this little piece of area, well, mass per unit area times area. No weird units or brand new physical quantities to try to make sense out of that I fundamentally don't understand. No, mass per unit area times area, that's mass. Mass is an accumulating. Mass is obvious. Mass, chop it up into little pieces. The whole is the sum of the parts. Mass is natural, right? And you can just talk about literally adding up all the little pieces of it. If this were Wyoming and I wanted to compute the population of or Colorado, whatever, I want to compute the total population. Well, people per unit area times area gives me people. And if I know how many people are in that box, and I can add up the number of people in each little box, that'll give me the total number of people. Right? So this construction here, where I look at one little piece at a time, and then I add up over all of those pieces, will allow me to attack just a tremendous number of problems. And so we'll draw the line right there. I think I may have gone over, if I know myself. Let's see here. Yeah, 40 seconds. Okay, see y'all later. Have a good one. And don't forget about attendance if you came in after I did attendance.
I just want to say thank you for your flexibility yesterday. I'm really sorry about that.
Hang on. I'm sorry. I just got to get this stuff.